Hey everyone, as an extension to our geometric progression, we're going to talk about the sum to infinity. Because we're looking at the sum, right, so we can use the series notation, and because we are looking at the sum to infinity, it means that we're going to add infinite number of terms, and therefore we have s subscript infinity. So we're looking at what conditions must there be for sum to infinity to exist. So that means that for sum to infinity to give an exact value, let's say for some k, there must be a certain condition fulfilled. All right, so let's explore that. All right, first let's examine the idea of what a sum to infinity is. So we know that a sum to infinity is basically adding an infinite number of terms, right? So adding infinite number of terms, all right, which is un, which means that if I add one more term at the end, right? One more term increasing, right? So that means, let's say if I added the nth term, I will add the n plus 1th term. I will still get s infinity equals to k, which means that only one thing, the term you added must be 0, right? And because of that, we have this conclusion. If as n approaches infinity, my term would then converge to 0. Alright, would approach 0, because that's how I can get back the sum to infinity, even adding an additional term in the progression, right? So this is the whole idea behind how a sum to infinity exists. Alright, so let's explore that further. Un approaches 0. Alright, so let's take a look at the formulas for our two progressions that we have learnt so far. We have AP being un equals to first term a plus n minus 1 times the common difference d. GP, we have un equals to first term a, common ratio r, power n minus 1. So now, let's take a look at what happens as n approaches infinity. Alright, so as n approaches infinity for the first one, we know that n minus 1 will approach infinity, and n minus 1d would approach infinity. So therefore, un approaches infinity. Alright, so the AP do not have a sum to infinity. How about for GP? As n approaches infinity, well, Rn minus 1 actually either approaches infinity or approaches 0. So let's see what happens. Right? How can R power n minus 1 approach 0? Now let's understand. For a solution, for a number to go close 0 by multiplication, it means that R must be a fraction. Alright, must be between minus 1 and 1, or simply mod R less than 1. Alright, because mod R is less than 1, R is between minus 1 and 1, it's a fraction, and it's making the absolute value of the first term decrease, right? It's basically making it decrease. So let's say I have a sequence, un equals to 3. Let's say my common ratio is half and minus 1. Then if you notice that I'll get 3 and then 3 over 2 and then 3/4 and then so on and so forth, it will decrease, right? But you'll never go below 0, but you get very, very, very close to 0. You can just try out for, like, let's say 3 half, let's say in power 98, sub n equals to 99. You realize it's a very, very small number. So this is the whole logic behind sum to infinity. Alright, as such, we kind of arrive at this conclusion. Alright, is that for sum to infinity to exist, S infinity exists only for GP, unless otherwise stated or otherwise proven, and that mod R must be less than 1, and is given as S infinity equals to first term A over 1 minus common ratio R. Alright, so let me draw the box properly. So let's look at some exact examples. So just now we had the example of 3, common ratio half, and minus 1. So we're going to apply the sum to infinity, right? Basically, first term 3 over 1 minus half would give us 6. Alright, 3 over half is simply 3 times 2. Now let's look at another example. Now it's slightly trickier. So let's say un equals to minus 1 over 3 whole thing power n. So don't be fooled. Firstly, get the geometric progression formula right. So I take out minus 1 over 3 times minus 1 over 3 and minus 1. My first term is a, my r is minus 1 over 3, while r is less than 1, therefore a sum to infinity exists. So first term, minus 1 over 3, 1 minus 1 over 3 basically means 1 plus 1 over 3. So I get 4 over 3 in the denominator, therefore minus 1 quarter. Alright, so there we have it, the sum to infinity for a geometric progression.